Good morning, students. Linear harmonic oscillator is a fundamental problem in quantum physics. It's a one-dimensional problem. And of course, we have seen one-dimensional problems earlier, like the infinite quantum well, finite quantum well, then potential barrier. And this is the last one in the syllabus. This is about linear harmonic oscillator. Harmonic oscillation we know already. So probably we would have studied in lower classes about a simple pendulum. So we have a bob which is attached with a small thread, and you are going to have some oscillation. So to and fro oscillation, back and forth oscillation, left and right motion. So these are all oscillations which we know already, and we have calculated the time period t or length or even g, acceleration to gravity. So we have calculated. So this will make harmonic motion. But here we are talking about linear harmonic motion. So this is the linear. So here linear harmonic oscillation, it means that the particle will undergo harmonic motion in one direction. So that's why it is called as linear. So it will make to and fro motion in one direction. So that's why it is called as a linear. So linear harmonic oscillator. So it's, as I said, it's a fundamental problem. And of course, we can study in classical physics, electrodynamics, statistical mechanics, solid state, atomic physics, nuclear physics, and particle physics. Everywhere it is the base. It is a fundamental problem. So it serves as an invaluable tool to illustrate the basic concepts and formalism. So how we are going to see how this has been formed. And of course, just now I said about simple pendulum. It's a very, very famous example for harmonic motion. And another example also this one. A spring, the weight is attached to the spring. And we are going to make it, just to pull the weight, it will make to and fro motion, left and right motion, about its mean position. So this is also a very famous example. And we know, just we'll think about simple harmonic motion using simple pendulum. And in a simple pendulum, there will be a bob. I am going to give a force, the bob will oscillate back and forth. So this is a starting point if you consider, and this is the ending point if you consider this one. Then this has to reach the ending point, again it has to come to the starting point to make a complete oscillation. This is called one oscillation, we know already. What is the potential here? The potential energy, suppose if you have a bob like this. So I am going to make an oscillation. This oscillation reaches the maximum position here. The potential energy is maximum here. The bob will stand at this position for a few seconds, again it will come back. Okay, that few seconds the velocity is 0. If velocity is 0, there will be no kinetic energy. Only potential energy alone exists at the end, that end. So when it comes back, it crosses the mean position and it has got the high velocity. So kinetic energy will be very high. It will be maximum here. What is the potential energy? It will minimum almost 0. Again it reaches the maximum potential energy. The kinetic energy will be 0. So this is what the kinetic energy and potential energy, there will be a distribution between them. So conservation of energy takes place here between kinetic energy and potential energy. So this is what the graph says. So this is the potential energy graph. Of course, when x goes to the maximum position and where the kinetic energy is 0, the potential energy is maximum here. Here also potential energy is maximum here. And these 2 points are called turning points in classical physics. So they are all called turning points. And this is a minimum potential energy where kinetic energy is 0. Correct? Is it correct? Kinetic energy is maximum here. Potential energy is mean 0. So kinetic energy is maximum. Only then the restoring force will occur. Okay. So when the bob goes here, and there will be a force which will restore its energy. So that's why it comes back. Comes in the opposite direction. So that's why there exists minus x, minus direction. Now corresponding graph can be shown here. The graph goes like this. Just see here, at these turning points. So they are all turning points. This is equilibrium point. The turning point, kinetic energy is minimum, potential energy is maximum. And at this mean position, kinetic energy is maximum, the potential energy is minimum. At this another turning point, the kinetic energy is zero, potential energy is maximum. So this is what the distribution of energy between kinetic energy and potential energy takes place. So conservation of energy. Similarly, you can take the another example. You have a spring attached with some other wall. The other end of the spring is attached with a small mass. I am going to pull it. So when I pull it, it makes some oscillation left and right, to and fro, about its mean position. So when it is very closer to this end, this is compression takes place. When it is away from the mean position, some elongation takes place. So there will be a compression and the elongation about its mean position. So this will also make some oscillation. But in the concept of quantum oscillators, we will talk only vibrations. We will never talk about oscillations. In classic physics, we will talk about only oscillation. That's a complete oscillation. Whereas in quantum mechanics, we will think about only vibrations. Vibrations of atoms in the solids, vibrations of molecules. We will never say this is an oscillation. We should not say. So in classical physics, it's an oscillation. Whereas in quantum physics, it's a vibration. So it's a vibration. Vibration about its mean position. So this is what linear harmonic oscillator is. And of course, just you have diatomic molecules. Just consider two atoms which is attached with a small bond. This bond can be considered as a spring. So there exists some bond length between these two atoms. So we can consider this a small spring, okay, between these two atoms. And suppose you have some vibration between these two atoms. Then again, the energy, potential energy can be drawn exactly like this. So you have two atoms now. Okay, atoms vibrate about its mean position if you consider. So when they are very close, so compression takes place, and this part of this one represents the compression. And suppose when the atoms move away, this is elongation. So this part of graph represents the elongation. The mean position is represented somewhere here. So this is where R naught. Okay. The diatomic molecule represents the blue curve. You just look at the blue curve, it is not harmonic. So this is not harmonic motion because this is not symmetry. Harmonic motion is symmetry. Symmetry about its origin, correct? About its origin. But here, look at this one. Look at the blue curve, which represents the potential energy for diatomic molecule, and it is not symmetry. It is asymmetry. This is called anharmonic oscillation. Anharmonic. So this is anharmonic oscillator. Okay. So this is for elongation and this is for the compression. And when look at this graph, we can have some approximation. So we can have anharmonic motion into approximation like this. So this represents a simple harmonic motion. So we are going to have some approximation. Anharmonic oscillation into harmonic oscillation. And especially when you look at the graph, about its mean position, they are the same. Exactly, they resemble. So at R tends to, at the equilibrium position, both are the same. Anharmonic motion and harmonic motion oscillation will be the same. So that's why we are taking the approximation. So this is about the vibration of diatomic molecules in 1D. And of course, harmonic oscillation, this is harmonic oscillation. Dotted curve is a harmonic oscillation. Blue curve is the anharmonic oscillation. So harmonic oscillator potential is a satisfactory approximation of small displacements. So this is a small displacement where both the oscillation coincides. Okay. Now we are going to look into the harmonic oscillator by means of an operator method. This is abstract method. Okay, operator method. So ladder or abstract method. It does not see, usually there are two avenues as I said. For quantum mechanics, there are two avenues. One is Heisenberg approach, another one is Schrodinger approach. Heisenberg matrix mechanism, Schrodinger wave equation. And in the syllabus, you are going to study only harmonic oscillator using abstract method. Okay, using abstract method, operation method, not wave mechanics. So of course we can solve the harmonic oscillator. What are the things that you are going to solve? We are going to get the wave function and the energy, like all the other models. We can get these two things by means of the first method, Schrodinger wave equation, as well from Heisenberg uncertainty method. But syllabus, your syllabus is framed in such a way that you are going to study only harmonic oscillator only by means of operator. So this is a ladder method or abstract method which we are going to see now, which deals with operators, operator algebra. And this operator algebra, there are two operators, one is creation operator and annihilation operator. So we are going to use a matrix mechanism and we are going to apply Dirac's notation, Dirac notation to solve eigenenergy value and wave function, corresponding wave function for this model. Okay. This method is essence a matrix formulation because it expresses the various quantities. We are going to get various quantities, creation operator, annihilation operator. As we said, it is a ladder. We said just now it's a method is a ladder method. Ladder we have steps are even, correct? In all the ladders, the steps will be even. So we have one by one, steps will be even. Either we can go up or we can come down using a ladder, correct? And here also we are going to use a creator operator which will lift from one state to another state even. Then we are going to have annihilation operator which will make us come from up to down. So we can go from down to up as well from up to down using creation and annihilation operator evenly. This is even space. So we can get creation operator, annihilation operator and x, the position, momentum and E in terms of matrices. So these are the quantities that we are going to calculate. Of course n also there. N is the number of steps in the ladder. So here number of states. So n also we can get. So this method is a more elegant method. It's very easiest method. It's a simpler method than that of Schrodinger wave equation and simpler than Schrodinger wave equation. Here we are going to consider a mass in the spring with the string constant from a classical harmonic oscillator. We are going to take an example. So now the equation goes like this. So you have Hamiltonian of a harmonic oscillator, which is the combination of kinetic energy and the potential energy. Okay. So kinetic energy is very simple. It's very simple, P squared by 2m. What is the potential energy? And potential energy, see, we have F equals minus kx, the restoring force I told you just now. When the oscillation takes place, the restoring force will keep the bomb into its original position. Okay. So that's why F directly proportional to minus x. So F equals minus kx, where k is a spring constant. And of course, the potential gradient of negative gradient of potential is equal to force. We know already F equals minus del V. And you combine these two equations, that will give you del V equals kx. Integrate on both sides. Integrate on both sides, that will give you V equals half kx squared. So V equals half kx squared. Your potential energy becomes half kx squared. Is it okay? So kinetic energy P squared by 2m plus your potential energy. Instead of V, you can substitute half kx squared. Put together, that will give you total energy. Is it okay? Now as we said that it makes to and fro motion, oscillation. So surely there will be a angular frequency. So omega equal to root of k by m, which we have studied already in the earlier classes. So omega squared equals k by m. Use just a substitute here. So your Hamiltonian operator becomes P squared by 2m plus half, instead of k, you just substitute omega squared m. So m omega squared x squared. Is it okay? Now look at this equation. You have momentum and this is your x squared. And it seems that there is a symmetry between momentum and position. See, there's a symmetry in momentum and position. This is also second order, this is also second order. So there's a symmetry between P and X. So it's given like this. So this particle now, as we said, this is a harmonic potential. This is a parabolic potential. Okay, this is a parabolic potential. So that's why this term is a harmonic potential. So the particle will oscillate in the harmonic potential. The problem is how to find the eigenstates. We are going to find out, and eigenenergy values of this Hamiltonian. Okay, so this is the last equation, H equal to P squared by 2m plus half m omega squared x squared. I am going to take the second expression, multiply and divide by m. We just multiply and divide by m, and that will give you m squared divided by 2m. 1 by 2m I can pull it out. So 1 by 2m I can pull it out. So remaining factor will be your P squared. So this can square, this can be squared. So I can write this as m omega x whole squared. Is it okay? Equation 2.144. Is it okay? What I have done is multiply and divide by m, and 1 by 2m has been pulled out, and I have written P squared plus m omega x whole squared. We know that a squared plus b squared equal to ia plus b multiplied by minus ia plus b. We know already this expression. You just compare these two and write in terms of that expression in terms of ia plus b. You just compare these two. So that can be written as ia plus b can be written as 1 by 2m ip plus your b will be m omega x. Is it okay? You compare these two and you can write exactly like this, ip plus m omega x. Similarly, minus ia plus b can be written as 1 by 2m minus ia. So here it is minus ip plus m omega x. Is it clear? It's very important. Is it okay? Now we are going to introduce two parameters. These parameters are dimensionless parameters. We are going to introduce. One is A, we call this as annihilation operator. Another one is the Hermitian adjoint of A dagger, which is nothing but a creation operator. So we are going to introduce these two parameters. These parameters are very important. These parameters will take us up and down. Okay, one is a creation operator, another one is a annihilation operator. So one is the lowering operator, another is the raising operator. It will rise from one step to another. Another one will lower from up to down. Okay. So A is a dimensional operator which can be defined as ip divided by root of 2h cross m omega plus x operator divided by root of 2h cross by m omega. As we said, this is a dimensionless. Correct. A is dimensionless. So this must be dimensionless. This must be dimensionless. But P has a dimension. We know already. You just calculate for the dimension of this. This will exactly matches with the momentum. So both will get cancelled. So that's the idea. You just go for this one, 2h per m omega. So just take the dimension of root of 2h cross m omega. H cross dimension for H cross will be ml square t power minus 1. M will be m. Omega equal to 2 pi by t. So t power minus 1. So t power minus 1. You just simplify. So that will give you m square L square t power minus 2. Take the root, that will give you ml t power minus 1, which is dimension of momentum. So dimension of momentum. So both will get cancelled. Similarly, just get the dimension for denominator of this expression. So root of 2h cross by m omega, h cross is this one, dimension for h cross is this one, dimension for m omega is this one. Both will get cancelled. You will get only L square. Take the root, that will give you L, which is the dimension of x. So which is the dimension of x. So this is the dimension of x and this is the dimension of momentum. Both will get cancelled. You will have no dimension. So it's clear that A has no dimension. So we are going to take the dimension parameter here. Two dimension parameters. One is for annihilation operator, another one is for creation operator. So one is plus, the other one is minus. Other things are same. Is it okay? Now multiply and divide by m omega. So that is in the second one. So this is A. Okay. What is this one? Annihilation or creation operator? Which one? Annihilation operator. A dagger is creation operator. So this is annihilation operator. So this expression, second expression you multiply and divide by m omega. See here, 2h cross divided by m omega. Multiply and divide by m omega. So that will give you in the denominator we have m squared omega squared. Correct? What is the purpose? We are going to make these two expressions same. So that's the reason. So m squared omega squared, pull it out, 1 by m omega. That will go to the numerator. So that will give you m omega x. You just take the common out. So 1 by root of 2h cross m omega. Is it clear? Multiply and divide by m omega in the second expression of the denominator, and you pull m omega out. So that will go to numerator. Just take the common term. So that will give you this. Is it okay? Similarly, you can also do the same thing, and for A dagger, you can get the expression. That is, multiply and divide by m omega, you pull it out, and this can be simplified, and you will get the Hermitian adjoint of your A, which is nothing but A dagger. Is it okay? A and A dagger. We have simplified. Now, we are going to multiply these two, A and A dagger. We are going to multiply A and A dagger, which will get very important result, which we want. A dagger. And of course, both are operators. When you are going to multiply the operators, order matters. So you can't change the operator. Okay, that's very important. So you have to keep that one in mind, and we have to multiply. Now this is A operator, this is A dagger operator. Okay, you are going to multiply. Multiply this term, that will give you 1 by 2h cross m omega. It's very simple. Now the remaining term. So remaining term is this one, and remaining term is this one. So you are going to multiply first this one, this one, second one, multiply ip with m omega x. M omega x multiplied by minus ip. So 4 terms we can get. First we will multiply p into p, that will give you p squared, minus is I into I squared, minus 1, so plus p squared. Okay, that's okay. M omega x multiplied by m omega x will give you m squared omega squared x squared. So simple one. Now next one will be ip multiplied by m omega x. So ip multiplied by m omega x. So px. Constant we can pull it up. No problem. The next term will be m omega xp. See, m omega m omega xp. Pull the common terms out here. m omega your px minus xp. And this term p square plus m square plus omega square x square, we will keep it this one as it is. Is it okay? Now we know already x comma p, which is equal to IH cross. We have already studied in the first unit. XP equals IH cross. But here it is px minus xp. It is just on the other way around. X comma p in the commutator will give you xp minus px, that will be IH cross. Now here it is px minus xp, that will be minus IH cross. So p comma x will be minus IH cross. Okay, you substitute for this expression alone, minus IH cross. So minus exists, and you have I into I squared minus 1. So minus minus will get plus, and you will have m omega h bar. Here also you have m omega h bar, both will get cancelled. You will get 1 by 2. Okay, so this expression will have 1 by 2. Just keep it in your mind. What of this one? P square, I pull just 2m alone inside. So that will give you p squared by 2m plus 1 by 2m. This m squared and m will get cancelled. You have m omega squared x squared. Is it okay? I have taken only 2m only inside. Remaining term h power omega, let it be. So we will get this term. This term is already, we know that this is Hamiltonian of the harmonic oscillator. We have seen just now. Okay. So this is. So this can be replaced with h hat. Okay. Is it okay? Now in the next one. So we can write this as h operator divided by h power omega. This will be 1 by 2. It's very important relation. So now this expression can be written as h equals h power omega a dagger. Pull plus 1 by 2 that side. That will give you minus 1 by 2. So a dagger minus 1 by 2. Then bring this term h power omega to that side. That will give you this. That's all. So you will get to 2.15 expression. Very important relation. H bar equals H bar omega A dagger minus 1 by 2. Similarly, we have multiplied with A dagger, correct? You just do your assignment as A dagger A. The same procedure. You will get the expression A dagger A plus 1 by 2 multiplied by H bar omega. That will be your Hamiltonian. So this is your assignment 1 in this section. Okay. So we are going to take A dagger A as number operator. So we are going to introduce this number operator. So earlier we calculated A dagger and we got the expression for Hamiltonian operator, correct? And similarly, you just multiply with A dagger A, you will get the expression for the Hamiltonian operator again. So this is for assignment, as I said. A dagger A is number operators. Very, very important quantity. You just remember. A dagger A is a number operator. It's a Hermitian operator. It's a number operator. Number operator will have the eigenstate ket n. Come on, I repeat. Number operator will have the wave function, will have the eigenstate ket n. Number operator. So for all number operator, there will be a ket n. So that will give you eigenvalue n with the eigenket. So it's an eigenvalue equation for the number operator. Number also is an operator. Okay, number operator, because this is number operator defined as A dagger A. It's an operator. So right hand side must be an operator. So that's why n is an operator. N operator, the eigenvalue of the operator is given by this expression. So number operator operates on the eigenfunction, will give you eigenvalue with the eigen function. Is it okay? Similarly, the Hamiltonian operator, H operator, operates on the eigenket. So that will give you the energy eigenvalue with the eigenket. Is it okay? Now look at these two eigenvalue equations. One is for number operator, another one is for Hamiltonian operator. Both have simultaneous, both have same eigenkets. Correct? Is it okay what I am saying? So both, they are all different operators, but they have same eigenkets, common eigenkets. If they are having common eigenkets, they will have simultaneous eigenkets. We call this as, and it means that both the operators will commute with each other. Very, very important concept in quantum mechanics. If two operators, if they commute, they will have common eigenkets. I am saying on the other way around. If two operators have the same eigenkets, they will commute. Is it okay what I am saying? So H and N will commute with each other and they have joint eigenstate. That's called common eigenstate. It means that if they commute with each other, if they have common eigenstates, it implies that we can measure both the things at the same time. That's very, very important one. At the same time, we can measure both N and H at the same time if they commute with each other, if they have common eigenstates, simultaneous eigenstates, joint eigenstates. Is it okay? So for a particular N, we can measure H, the Hamiltonian operator. We will get the eigenenergy for a particular N simultaneously at the same time, because they commute with each other, because they will have common eigenstates, eigenfunctions. Okay, is it okay? Now first we will go for, let us derive the commutator A dagger. Okay, we are going to get the what is the value. A dagger can be written as A dagger minus A dagger A. First we will calculate. So this will be your A dagger minus A dagger A. So A dagger minus A dagger A. Okay. So we will have a common. These things are common. So you pull it out. So we have pulled out. Now we are going to multiply this one and this one, this one and this one. We have 4 terms here. Here also 4 terms. Very simple one. Already we have done earlier. It's very simple. First we will multiply. So this will give you p squared. We will multiply these two. That will give you m squared omega squared x squared. Then ip multiplied by m omega x, that will give you px. M omega x multiplied by ip will give you this. Is it okay? Now next one. Minus ip multiplied by p, that will give you p squared. And you go minus in here. See here. Minus ip multiplied by ip will give you minus I squared p. I squared is minus 1. So plus p squared. This is minus is there. So that's why minus p squared. Clear? Then now m omega x multiplied by m omega will give you omega s. So m squared omega squared x squared is minus is there. So minus. Similarly, you can go for another term. Minus ip multiplied by m omega xp px with a minus sign, so it will become plus sign. M omega x multiplied by ip will give you xp, here minus is also minus. Is it okay? Now just take it off the common terms. So p squared will go off, m squared omega squared will go off. We have only 4 terms, remaining 4 terms. You pull common terms out, I omega, im omega, px minus xp. And here im omega, px minus xp. Px minus sp, already we know that this is minus ix cross. You substitute here. Okay, minus ix cross. So already one I is there. Here I. So that will become plus. So you will have m omega h bar. Here also this will become plus m omega h bar. That will give you 2m omega h bar. And you just shake it off. That answer is 1. Very, very important relation. A dagger minus A dagger A equals 1. Very important relation. Often we'll be using this one. So A dagger, the answer is 1. Okay, any doubt on the screen, on the slide, up to equation 2.163. Okay, so our A dagger answer is 1. We will be using often this relation, so you just have it in your mind. So now we know that we have to calculate matrix of the Hamiltonian. We are going to diagonalize in order to obtain the energy eigenvalue. This is what the ultimate aim is. We are going to find out energy eigenvalue and wave function. And of course, we are using only matrix mechanics. For the matrix mechanics, we have to diagonalize to get the energy. So this is the idea. For any matrix, in order to get the energy eigenvalue, we have to diagonalize the matrix to get the energy, diagonal elements. These diagrams will give you energy eigenvalue. Okay. Now we are going to use the eigenvalue equation. So this for this operator, this is annihilation operator. So H operator operates on annihilation operator. That will give you energy eigenvalue with the annihilation operator. So we know the eigenvalue equation very well. Okay. So just listen to me. It's very important concept. So I can write this as H operator operates on the annihilation operator. We know already for annihilation operator we have already got this expression H power omega A dagger minus 1 by 2. Previous slides. You just substitute here. So H power omega, you substitute this one. A psi will be somewhere here. Is it okay? Now from right, this operator operates. Correct? So this can be written as A dagger A minus A by 2. Is it okay? This operator. Now I pull A to the left. So this A comes here, this A comes here. So this will become A dagger A minus 1 by 2 psi. Is it okay? This expression? Fine. Now A dagger A, just now we have calculated that A dagger minus A dagger A equals 1. So this expression will be like this, and A dagger A will be A dagger minus 1. Correct? So instead of A dagger A, I can write A dagger minus 1. I can pull, just listen to me, H power omega A with minus 1 alone. So this will give you eigenvalue. This multiplied by minus 1 will give you eigenvalue. This is a value. So H power omega with minus 1 alone I can pull it out. Remaining I am going to keep it. Is it okay? So I have pulled only H power omega alone out with a minus 1. So remaining factor I have written like this. I repeat, see here you have, this is an operator, they are not going to disturb anything. This h bar omega multiplied by minus 1, this is minus h bar omega, it's a value, I can take it out, it's a number. So I have pulled out minus h bar omega with the annihilation operator plus the other term, a dagger minus 1 by 2. Is it okay? Now this minus h bar omega I can do like this. This of course a is here, and what of this one? This is your h. This term a dagger minus 1 by 2 your h with h bar omega. So instead of this term I can write h. So minus h bar omega. This term can be written as h. So we can write minus h bar omega plus h can be written as h minus h bar omega. Correct? And h psi equal to E psi. So this will become energy eigenvalue. I can pull n eigenvalue out together, E minus h bar omega, and A psi will go that side. Is it okay? I can get only after making this term into the operator into that side. Come on, is it okay? H psi equal to E psi. Okay, so this will become as E. So E minus h bar omega, it's a number, I can pull it out. So E minus h bar omega, this operator will go that side. So it implies that the Hamiltonian operator operates on the annihilation operator. Okay, the Hamiltonian operates on the annihilation operator will give you E minus h bar, that's the energy minus h bar. This is 1 h bar. It reduces the energy by 1 h bar omega. It implies that the annihilation operator will reduce the energy by 1 h bar omega. It implies. So this is called annihilation operator, lowering operator. It lowers the energy 1 h bar omega. So A decreases the energy by minus h bar omega. It decreases by h bar omega, 1 h bar omega. So A is called a restriction operator. A is the annihilation operator, the lowering operator. Is it okay? Similarly, you can also do E plus h bar omega when you operate the creation operator. So that will become E plus h bar omega. Okay. So now we are going to do the same thing. So H operator operates on creation operator. So this is creation operator will give you En with a creation operator. So now we know that H equals h bar omega, A dagger A plus 1 by 2 we know already. You substitute here. So instead of H you just substitute here. So we can substitute. Now this operators from right to left. Okay. So that will become A dagger A. This A dagger comes here and this A dagger by 2. You pull A dagger to left. The same technique. So A dagger left. So that will give you A dagger. The remaining thing will be A dagger plus 1 by 2. Is it okay? A dagger plus 1 by 2. So we can write A dagger equal to 1 plus A dagger A using that expression. A dagger which is equal to 1. So 1 plus A dagger A. Now you pull 1 out. The same technique. This is a value 1. This is the eigenvalue h bar omega. And you pull h bar omega multiplied by n will give you this. Remaining term A dagger plus A 1 by 2 will be this we have written, which is nothing but your h. The same method. So this will be your h bar omega A dagger, this h bar omega plus h, and here A dagger is left side and psi is on the right side. Now this is your the value for eigenvalue will be E plus h bar omega for this operator. H psi equal to E psi. So E plus h bar omega. Now this A dagger goes that side. So you have H operator operates on the creation operator that will give you eigenvalue with a creation ket. Is it okay? A dagger side. So what does it mean? It raises energy by 1 h bar omega. So like a ladder. I said it's equally spaced. For all the ladders, it's for an ideal ladder, it must be equally spaced. So we can go up and come down. So here also go up in the sense 1 h bar omega we can go up. Similarly 1 h bar omega we can come down. If we use the suitable operators, creation and annihilation operators. Is it okay?